the biodiversity loss that we're seeing, the climate change we're seeing, and pollution, a triple planetary threat. At Fenner School, we're really lucky to have some of Australia's best researchers, and probably even in the world, in biodiversity loss and indeed in climate change. And yet pollution is something that is poorly covered not only at ANU, but actually at Australian universities in general. But luckily for us, despite this paucity in undergrad research, we actually have some very good postgraduate researchers. And one of the best in the business is Brad Clark. So Brad is from the University of Melbourne's Australian Laboratory for Emerging Contaminants. He's the only person currently who can analyse PFAS down to the US EPA guidelines in Australia. I think that's still right.
Depending on which limit you
Depending on which limit you use. He works on emerging contaminants around Australia. He's definitely one of the nicest people in the business too. So I'm so lucky that he's here to teach our course, Pollution and Practice, which is a third-year course. It's an intensive running right now. And we're very lucky that as part of that, he's agreed to do a public lecture for us. So please give Brad a warm welcome.
Thank you very much, Jules. It's almost worth coming to give the lecture just to get that introduction. Some of the things I hear about myself, so thank you very much. Yeah, I'm a senior lecturer at the University of Melbourne. My expertise is based on pollution. I'm going to talk to you today about PFAS and microplastics, and actually the bigger issue of chemical pollution. I'm going to start with a quote. For the first time in the history of the world, every human being is now subjected to contact with dangerous chemicals from the moment of conception until death. It's a frightening reality that we currently live in, and I'm going to tell you who said this quote at the end of my talk. I'm going to start with some facts and figures too. Pollution is the largest environmental cause of disease and premature death in the world today. Pollution causes roughly 9 million deaths worldwide each year, or equivalent of 1 in 6. And it's responsible for more deaths than AIDS, tuberculosis, and malaria combined, and 15 times more than from wars and other forms of violence. This study was prior to the conflicts that we're seeing in Europe and the Middle East. And chemical innovation. What we've seen in the last century and modern society is grounded on a foundation of chemistry. It's humanity's ability to manipulate matter that allows us to have a lot of the conveniences that we really enjoy in modern life. And that convenience has come at a cost. And in actual fact, when we look at the 3 biggest transformations in modern society, energy, polymers, synthetic chemistry, they're all driven by the same fossil fuels. And you can see that you have this widespread destruction, or you have climate change as the opposite of energy. Polymers, which have, we have a new geological age now because of polymer, and we're going to see chemical manufacturing dramatically increase. And one of the perverse outcomes that I predict will happen as we move away from fossil fuels is you'll see that a more production put into chemical innovation and also polymer production. We are seeing that the chemical industry is expanding rapidly. So we're seeing massive increases in the amount, type, and quantity of chemicals that are being synthesized. Concerningly, we used to think there was around 110,000 unique chemicals for used in modern society. That number's actually closer to 350,000. Many of them we don't know what they are. So they're confidentially described in government databases, or they're ambiguously described. So up to 120,000, we actually don't know what they are. We've seen a regionalization of chemical manufacture as well. So we've seen countries that traditionally made a lot of PFAS, for example, in the US, have now moved to other regional economies, initially China, but also other emerging economies. What we now know is that the chemical profile in each country will be really unique. And this means that it's really important that the Australian government has its own chemical management approaches, because we cannot just simply rely on the work that's being done overseas. Some of the worst impacts of exposure to chemicals includes cancer, reproductive health problems, impaired immune systems, and neurological damage. You all have synthetic chemicals in your blood and your body. So you'll have a range of persistent organic pollutants in your fat, and then you'll also have a range of fluorinated chemicals moving through your body and your blood. And the first generation of OCPs and PCBs, we dealt with things like toxicity, and then we started to learn about endocrine disrupting chemicals. And that's really what our Stolen Future talks about. It shows the more chronic effects of exposure to chemicals. And this study really typifies, I think, what we're looking at, and which can be the cognitive damage that can occur from exposure to chemicals. So this study's found in side-by-side villages in Mexico that children that were exposed to pesticides suffered cognitive damage. This will probably be lifelong issues associated with their intelligence. So reduced IQ is also an effect of particular chemicals. Just last week, we saw that there was a relationship between bisphenol A exposure with mums and autism in the boys, the children. And so the consequences of chemical exposure are significant and serious. In actual fact, it comes at a huge economic cost to us as well. So I started to realize that people probably weren't listening to the message. And then I thought, how do you convince the government they should do something? And I thought the only way is an economic argument. And so I started looking out economic arguments to try to explain the costs of the health impact. And when I found these numbers, I'm like, that can't be right. And so the first one there is when we eliminated lead from petrol and paint, it estimated that there's 2.4 trillion in annual health benefits. That was $1 trillion of health benefits. We estimate that the welfare costs associated with pollution are in the order of 4.6 trillion per year. And that accounts for 6.2 of global economic output. When we look at the effect of endocrine disrupting chemicals, so things that interfere with our hormones, so all of those effects that I talked about before were EDCs, and using only a small subset of chemicals there's a consensus agreement on that they cause effects and a consensus on the effect that they cause, it's thought that the annual healthcare costs in the US is around $340 billion per year. If we just invested a small fraction of this into preventative work and remediation, we'd be saving ourselves a lot of money. Okay, so I guess I have a little message and I have a little story as we go through this. It's this tension between advancement and modern society and the impacts. And that's really what we need to figure out how to balance this properly. And it really starts with DDT. DDT was the prototype pesticide, and it became to symbolize modernity. It was originally thought to be non-toxic, and its persistence was a valued property. It was thought of so highly that the person who discovered insecticidal property was actually awarded a Nobel Prize for this in 1948. The evidence of harm, let's see if this works. Sometimes it works and sometimes it doesn't. Anyway, so the folks this morning got to see a little YouTube clip. What it is, so what happened was back in the day, Mum would make dinner and then spray the table with DDT. And that was sort of a practice that was considered acceptable. And so you can sort of see the fog outline in the background there. That's actually a table with children about to eat dinner. This, as far as we could tell, was reasonably common practice. And the Silent Spring really captured the attention of the modern environmental movement and is credited with giving birth to the modern environmental movement. And because what Rachel Carson did was she cataloged just what she was observing, really, the death and destruction that was raining down from the widespread application of pesticides into the environment. We saw heavy impacts on aquatic ecosystems, dead fish kills. What we also saw was rampant spraying of pesticides through pristine environments and suburban environments. And then as rain would fall on this pesticide, it might create toxic soups. The pesticide would accumulate in earthworms. Earthworms would eat the birds would eat the earthworms. They would die, and that's what we were referring to as the silent spring. All of the life that we would associate with spring had been poisoned. Generation 2, it's not maybe generation 3, I'm going to call it generation 2. So we learned a lot of lessons from the first generation of persistent organic pollutants. So these are chemicals that accumulate in our body, they persist in the environment, and they're also toxic. So now we're up to PFAS, and I've called this a little case study of innovation gone wrong. But we're seeing a story here that's being repeated over and over and over again. And I can point you to all sorts of different chemical classes where we see this. So PFAS really grew out of the Manhattan Project. So that was where we created the atomic bomb. And so what we found was an inert material that found its way into the home. And so it found its way into the home, firstly, as your non-stick fry pan and other materials that were non-stick. You may have heard of Teflon, Gore-Tex, Scotchgard. You may have even sprayed your shoes with Scotchgard at some point, or your couch. If you look at the back of your cupboard, if you haven't moved in a while, there's probably a can of Scotchgard in there, and it'll have PFAS in it. We actually recently became aware that the manufacturers of so 3M and DuPont were aware of the toxic effects of their products as early as 1970. It wasn't until 2001 that really the scientific community became aware of not the toxicity, but the evidence of environmental contamination. So you all have PFAS in your body. We all have a level of PFAS in our body. And it's what I refer to as omnipresent. So it's in, as far as we can tell, almost every living organism on the planet and most environmental compartments. What we saw was a voluntary phase out of particular types of PFAS. And then we saw what we've now seen is rapid chemical innovation to replace those PFAS. So we used to have 2, then it went to about 30, and now it's around 15,000. Now, I know there's not a heap of chemists in the room. There might be some. This is a basic structure of this part here is the perfluoro part where we have fully fluorinated. So that carbon fluorine bond is virtually indestructible. So there's no, as far as I'm aware, there's no natural CF3 bonds in the environment. TFA possibly is naturally occurring, but it mostly doesn't exist. And this part here is what's referred to as a polyfluoroakyl substance, it mineralizes. So in the environment, this will degrade to this. And so now we have they're called precursors. So we have a lot of compounds that have been introduced that will transform in the environment to things that we are regulating, we care about. And one of the issues here is that this is just a way of skirting the problem, because as soon as I add a different atom to my molecule, I need a different analytical technique. I need a different assessment process. I need a risk assessment. So the whole thing is out of control. So what do we know about the C8s? The main 2 are PFOS and PFOA. So PFAS seems to be in the news almost every week at the moment. And what we're concerned about in Australia is PFOS. It's the one on the top. The main way that it got out into the environment was through the use of firefighting foams at our Defence Force sites as a training exercise. We'd set jet fuel afire, we'd put it out with our AFFF, and then it would leach through the groundwater and contaminate the drinking water supplies. It's what's referred to as a multi-system toxicant, which means that the effects of PFOS or PFAS on the body are, they're not confined to one location or one specific mechanism of action. There's been a lot of work founding associations. So what you need to move forward from association is mechanistic studies to show that they have these effects. But there is a high certainty of a relationship between kidney and testicular cancer and increased cholesterol levels. We know that PFAS are persistent, mobile, and bioaccumulative in the environment. So what about Australia? So we've seen in the news three main areas of contamination: Oakey, which I've spelt wrong there, Williamtown, and Catherine. And these were areas where the Defence Force had contaminated the groundwater in those areas. And they were issued statements. They were told not to drink the local water, minimize groundwater for bathing, showering, swimming pools, minimize consumption of homegrown produce in these areas, so fish, red meat, eggs, and poultry. And the other main one that you might have heard of is Fiskville, where this was a CFA training site, and the firefighters in these locations, they believe that they've had health outcomes associated with exposure to PFAS and other materials there. There's debate still in all of these locations about whether there's actually health effects from exposure to PFAS. I'm going to also talk to you about one of the things that we do with sewage sludge. So anything we use in society will probably find its way into two places: wastewater treatment plant or landfill. And then even landfill will eventually find its way back to wastewater treatment plant. So it's likely to find its way back to the environment in some way. So biosolids is the residual of wastewater treatment plants. We use it as a fertilizer in many countries in the world, including Australia. 70% of our biosolids are applied to land. It's an incredibly risky and dangerous practice because all of our trade waste also goes down here. What we've seen in particular locations, one was in Germany and one was in Alabama, where organic amendments have been applied to as a soil improver. It resulted in contamination of drinking water of about 5 million people, between 50,000 and 5 million people, greater than 500 nanogram per litre, which is a very high level, particularly in today's context. And we see a similar story in the US, where these local treatment plants are accepting trade waste from 4 different fluoropolymer manufacturers, and it resulted in 25% of the state's drinking water being contaminated. And so this is something that we should be really very mindful of as moving forward about the role wastewater treatment plants play in the movement of chemicals. So the main sources of PFAS are industry, Defence Force, and airports. And then we're actually going to need new terminology similar to lead to describe PFAS and thinking, because we've managed to contaminate the environment to such an extent that there's no area or environment free of PFAS. So we have the domestic environment is probably our biggest exposure source at the moment. We have wastewater treatment plants, and then we have landfill. So I'm going to show you some of our data today. We'll start with wastewater treatment plants. And just before I do that, I'm going to talk to you about the substitution problem as well. And so what we've seen is a lot of really innovative chemistry coming through this space. And so we originally just had these sort of straight chains. And now what we're starting to see is these cyclic variants up the top. We start to see some mixed halogenated. So they're chlorine, bromine, fluorine, they're all halogens. And so they tend to be associated with persistence. Ether bonds as well. And so all of these now are finding their way into the environment. You'll have seen a lot of discussion of the drinking water guidelines around in the media, and about why Australia's levels are different to particularly the US. And that's something that the NHMRC is currently reviewing. So they're looking at the health-based decisions that underpin your regulatory values. So one of the things in ours is that we have a combined total of PFOS and the 6-chain level at 70 nanogram per litre. While it's not explicitly stated there, I don't believe, the the assumption here is that the mechanism of toxicity of these two types of sulfonates is consistent and additive, which is in some ways it's a little bit of a different approach to how other countries have done it. But what we've been observing is that as regulations have been more adopted, they're always going lower. There's not been an instance where we've actually elevated them. So the evidence is more consistent that there are health outcomes from exposure to PFAS. I'm going to show you some of our data from different studies, and references are down the bottom. And if you would like a copy, you'd be most welcome to contact me and I can send it to you. This one was a study where we looked at PFAS through wastewater treatment plants. So PFAS at wastewater treatment plants are a known emission source of PFAS to the environment. So when the original guideline values came through in Victoria and EPA, they had a value of less than 1 nanogram per litre. And this sort of scared people, because what it meant was that there's no way that you can discharge effluent into the environment without exceeding this value. So all of a sudden, all wastewater treatment plants were exceeding an ecological threshold value. So that was the basis for people wanting to do a study with us. So we looked at the range of PFAS in effluents around Australia, 19 different treatment plants, looked at influent and effluent. We actually looked at all of the parts through the treatment process itself. If you compare the mean of the influent and the effluent, you can actually see there's a difference. So it's 90 versus 140. In actual fact, the range is changed too when we look at the sum total, which sort of suggests that there's a formation of PFAS through the treatment process. And that's exactly what we found. So, and it's what you would also predict to happen. So what's actually occurring through treatment plants is that there's an emission of precursor PFAS. When they get to the treatment plant, that polyfluoroakyl part is degrading, and it's forming the ones that we regulate. So the carboxylic acids. And so we see, and so what I've got here is these are all just the carboxylic acids, and we've got varying chain lengths, 4, and that's up to 10, and then we keep going. And for all of those ones, what we see is that there's a statistically significant difference between the influent and the effluent, showing that they're being formed. It also shows that we're not also measuring the right precursors, so we weren't able to link them with the type of the precursors that formed them. I think this was a really cool study, and this was done by Dr. Drew. What we did was we took influent samples at a wastewater treatment plant in Melbourne every hour for a whole week. There was about 200 samples we ended up processing. It was an extraordinary amount of work. Takes us about a day to process 12 samples, so it took us a long time to process them all. Now, typically, when you do a wastewater treatment plant study, what you would normally do is you probably sample on a Wednesday, because that's when the operators are available. Or maybe you spend Monday and Tuesday preparing your bottles, drop your bottles up, get your sample on the Wednesday, get it back, and then do your work. You might get a 24-hour composite as well, maybe on a Wednesday or a Tuesday. And so we wanted to look and see if there's any variation in the days of the PFAS through the treatment process. And so what we've got here is Monday through Sunday. And you can pretty clearly see that there's actually a difference in the day of the week that you take the sample. Now, this is really important because this actually demonstrates, not just for PFAS, but for any sort of pollutant work done on wastewater treatment plants, that you really need to be very mindful in the day that you take your sample. And the other thing that was super important is in this graph here. So this is still Monday through Sunday. We actually see 2 pulse events of PFAS. And we see a pulse event on Friday night, and we see another pulse event on Saturday morning. And then the rest of the time we see very low levels. So if I start with this bit, your homes have PFAS in them, very low levels. And this is the PFAS that's coming from our homes. So we can actually use this now to calculate the background level of PFAS that will be emitted to the environment from all of us, from our homes. This part becomes really important now because I can tell you what's being elevated or what's being introduced. So one of the easiest way to stop pollution is to stop it at the source. So if I can, this is probably one emission source. It could be a couple, but it's probably just one. It's probably a factory in my guess that has a really great surfactant that cleans up oil like nothing else. And they're just using it. They're using leftover. That's my guess. If we can find that emission source, we can save ourselves millions of dollars in treatment costs. And so it's probably a similar story in treatment plants around the country. By the way, as we go through, I'm more than happy to take questions as we're going through. PFAS in biosolids. Now, analytical chemistry is the foundation of which we can understand the environment. And I bang on about this a lot. And if you don't, there is a bit of luck with analytical chemistry, particularly the way that we build our, what they call targeted analytical chemistry methods. Because, well, actually the reason we had that compound in here is because one of the students told me it was a new one and he wanted to buy it. So I bought it. So we added it in to our method. Our methods can't see them unless I have a standard. That's how it works with analytical chemistry. Well, there's a new style coming through, but I think that might get a bit too confusing. But anyway, so essentially it's blind to anything unless I've trained built my method around. And so we'd added in these new compounds into our method before we did this big study of PFAS in biosolids. And if we hadn't have added these chemicals in there, it would look like the levels were much lower than they actually were. And one of the ones we started to find were these things called DIPAPs. What's a DIPAP? Now, a DIPAP is something that's put into food packaging materials. And so a DIPAP has two perfluoro sections, and then the middle of it has a mineralizable section. And so for every one DIPAP, it's going to break apart and create two of the carboxylic acids that we're regulating. And so obviously that's a big issue. And I think what it also does is speaks to, we're creating a ticking time bomb of precursors of PFAS in our biosolids, and now we're putting it onto our agricultural soils. When we think about biosolid land application and the latest PFAS NEPM has proposed limits finally on biosolids, is that it's an unnecessarily risky practice for Australia to engage in. And the underlying concept is that it is relying on the natural attenuation processes of our soil to detoxify all of the chemicals that are in there. And the evidence doesn't support that this will actually occur in reality. I'm going to talk to you a little bit about this study. So we wanted to do some work where we looked at, if you had a resident bird population on a contaminated water body, what would be the impact, or really what was the level of PFAS in their body? Actually, it was a wastewater treatment plant were the people that wanted to answer that question. But the problem is most birds fly and they move. So you can't necessarily link the environment with the levels that you're observing in them. So we gave it a bit of thought and we're like, right, where can we find a resident population of birds that we know don't move? And that led us to Albert Park in Melbourne. Now, Albert Park, you may have heard of, is the home of the Grand Prix as well. And so what we went and did was when we went and captured swans. I think we got ecologists in the room today. So people, getting swans, it feels a little mean, but you draw them in with your bread, get them close to the jetty, and you grab them by the neck. We have permits and everything, and I had an actual professor of swan handling with us, very famous in the area. But so we let him do that anyway, and then we took their blood. We also took some feces as well, and then we took every part of the environment around there as well, and then we gave them some bread and let them on their way, so they'll be happy. And this was our results of the water. So we had different sites from around the track. We had water, sediment, and their food as well. And you'll notice this one here. So Drew had just asked me to buy this standard for him as well, and we just put it into the method. And it was that cyclic one I showed you before. And if we hadn't have added that to the method, we wouldn't have known. And the other thing that was really interesting about these samples is these are some of the highest urban PFAS levels that we had seen for, actually ever from our group. Now, what was really important, there's actually a number of really important factors in this study. And this is one of them. When you do ecological studies, you don't really want to have to kill your samples unless so with the birds, what we actually showed was there's a correlation between the feces and the internal blood levels. This means that you can actually sample the feces in order to get your first measurements of PFAS in birds. That's a really important finding. You can see that relationship holds very true for the 4 main PFAS. The other thing that really came out of this is, where is this chemical coming from? Now, we've done a follow-up study on this. So the levels in that original study were about 20 nanogram per litre. The levels, we just done a study this year where we sampled every single day for a month before the Grand Prix and a month after the Grand Prix. And they didn't change much through that time. And they were much higher this time than they were at this initial study. So we're not sure where it's coming from. We originally thought it was coming from the Grand Prix, but our hypothesis was if the Grand Prix was the source, we'd actually see this elevated level through the middle of the Grand Prix, and we didn't see that. So the other thing that's really important about this study is actually shows you can use contaminated urban environments to generate fundamental data on the behavior of chemicals, so how they bioaccumulate. And that's one of the things we got from this study. We were able to put out the first bioaccumulation factors of that cyclic PFAS. PFAS in blood. So typically what will happen when you regulate a chemical, you'll see a decline in that chemical in the population. We see it with DDT, we've seen it with deodorant, we've seen it with PCBs, now we're seeing it with PFAS, we're seeing it with PFXS and PFOA. We know that there's we know that there's a pretty typical profile in terms of if you're contaminated. So if your drinking water is contaminated, we'd expect you to have elevated PFAS in your blood. We've been working on a self-sampling device. So all of the data that's generated in Australia is a little bit confounded by the fact that it's all pooled blood samples and it's all ex-pathology samples. So it's something that we don't really need to be doing anymore because the analytical chemistry has advanced so significantly. So what we've actually been working on is a self-sampling device. It's called a HemaPen. Actually, you can use other devices too, where you take it's like a glucose test. So just a small prick of blood, and then it's 11 microliters into this device. You can mail it back to us and we can report the levels of PFAS in your blood to a very low level. This is the level of PFAS in my blood. So one of the arguments is that people have made in the past is that individuals shouldn't have the right to know the level of pollution in their blood. I don't think that's a reasonable argument anymore. With the persistent organic pollutants, in some ways there's nothing really you can do about it. But with something like this, you actually can now do something about it. If you had really elevated levels, you could change your exposure situation. You can look at your house or whatever it is that may be causing those elevated levels. And in actual fact, you can have preventative screening for diseases that are associated with these chemicals. And you could probably also, I'm not saying donate blood, I'm calling it bloodletting. So get the leeches out. You can actually that's one way we know to actually reduce your body burden. Now, my levels are really typical. They're actually sitting around the mean of the Australian population. The thing that I'd also like to draw your attention to is that I have a number of chemicals in my blood that are reported in Australia for the first time. And so that one, I think I showed you, was that one, that was the chlorinated one that was replacing PFAS. And colleagues of mine in America are reporting a very similar thing. They're finding that chemical that, as far as I'm aware, has only ever been used in China, finding that in their blood as well. And so while we're seeing these ones coming down, the question is what's going up? And there will be something because of the chemical substitution problem. And we need to be having appropriate human biomonitoring studies. So at the moment, Australia doesn't, apparently the Australian Bureau of Statistics has started to do some pollution biomonitoring. I want to follow that up and see this. But many other developed countries have coordinated annual or biannual pollution biomonitoring studies. We should have the same thing. It's really important. And it shouldn't be based upon pooled samples. It should be individual samples with many communities and representative across the whole country. The thing about PFAS is it distributes into your blood into different ways. So we need to understand how it distributes in your blood. And this isn't our work, but this is pretty frightening. UOF is the unexplained fluorine. So a big portion of the organic fluorine in our blood, we don't know what it is. Now, it is possible it's a pharmaceutical or some other chemical, but it's also possible it's an industrial chemical. We should be doing more work to understand what these chemicals are. By focusing on the humans as well as the human biomonitoring piece, we can focus on the biologically relevant chemicals rather than, say, doing work on the environment first. Start there and then work your way backwards. Okay, that's PFAS, PFAS 101, or some of our work. I want to talk about microplastics for my final 7 minutes. Is that right, Jules? Ubiquitously detected throughout global air, water, and soil. You cannot find an environment now that doesn't have plastics. Top of Mount Everest, bottom of the Mariana Trench, Arctic, Antarctic, anywhere you look, you'll find microplastics. About 5% of the plastics that we generate each year is likely to end up in the ocean. And it's estimated that these numbers are a little bit out of date, but 5.5 trillion pieces of plastic debris, that number will be a total underestimation. There's thousands now reports of interactions of animals with interactions with wildlife with plastic debris. And plastic waste is now so ubiquitous in the environment, it has been suggested as a geological indicator of the Anthropocene era. So what we really need to understand, what are the sources, exposure, and impact of microplastics on human health and the environment? Microplastics captures people's attention like no other issue. And the reason is you can see it. And we can clearly see the environmental impact when we've done it wrong. It's lovely being in Canberra. It's one of the cleanest cities we've been in. And we were just commenting last night, there was no graffiti, even in the underpass. So we're very impressed by that. Well done, Canberra. So we see images like this that are quite gut-wrenching. This is the one that I always draw my attention to. It's a shearwater fledgling. Its parents have gone out into the ocean. Mum and dad will forage for food. They'll bring it back to the nest. They'll regurgitate up the food, and they'll feed what they think is food to the young, and it's actually plastic. The young doesn't have the ability to regurgitate, and it starves to death. And so we'll see remains like this in locations. And I think this is a very sad indictment of humanity's legacy. There's a lot of talk about the circular economy. Now, I think we should be approaching the circular economy with a lot of caution, because if we move too quickly into this, what we're likely to do is start creating a concentrated cycle of chemicals, particularly things that we might become exposed to. And in some ways, it's also a Band-Aid solution for a bigger problem. So people tend to think if we recycle it, it's not an issue. Perhaps the better way would be to not produce it in the first place, or look at the look at the things that we want to have as our conveniences and say, well, you can't have that coffee cup, Jules. You should bring your own keep cup, or you should take 5 minutes and have the coffee at the cafe. I'm not sure what we're in such a rush for, not just you, all of us. And so essentially what we're doing with this whole process, we're really delaying the inevitable. It's all going to end up in landfill. And landfill is in some ways something that we're requiring future generations to deal with. And one of the big issues in plastics, and sorry to get too analytical chemistry and nerdy on you, is that there's a real lack of reporting harmonization. So there's a lot of different size ranges that are being used. And what this means is you can't compare international data. And so if there's a lack of coordination on reporting, that really prevents us from doing literature reviews and studies comparing international findings. The other thing that's really complicated with plastics is if I'm just measuring PFAS, I'm just measuring PFAS. When I'm measuring a plastic in the environment, I've got different sizes. Then I might have a different additive. Then I might have a different color. And then I've got a different polymer. Like all of these things matter in terms of its ecotoxicity. In fact, and then if you see this one here, this little category here, so we might have spheres or we might have shards. Now the spheres are actually less damaging to the environment than the shards or to the animals that ingest them. And so we have actually this cascading issue of problems with the analytical chemistry. And the other one is that it's not just polymers. Actually, plastic's really a complex mixtures of thousands of chemicals. And so it's up to 15,000 now plastic associated chemicals have been identified, including bisphenol A that I just mentioned before. I think I mentioned this morning. Anyway, and we see all of these different chemicals. Okay, so I'm going to show you a little bit of data and then I'll end up. So Suba is the fellow who did this study. We were actually asked by a local high school. They were concerned about wastewater. They were concerned about landfill leachate contaminating their environment for PFAS. So we went out and monitored the bores for PFAS. Suba had built a method for microplastics in groundwater. And he goes, can I come and collect some samples too? I'm like, sure. I don't reckon you're going to find microplastics in the groundwater, but if you want, come along. I was wrong. There were microplastics in the groundwater. We were the first in the world to report this. And this is important because it actually showed, and since we've seen studies that have demonstrated this, is that plastics will move through the soil profile into the groundwater. It's also showing the ubiquitous nature of the plastic pollution problem. And there's really no way we can ever remediate the plastic in groundwater without taking it out. So the legacy of this pollution will outlive us all. And we also did another study. We looked at microplastics in drinking water bottles. So we found them in most bottles that you would drink. And so typically when they make, when you make a bottle, it's often blown apart and then it will be sealed together. So you'll see it on the inside, there'll be like a little edge to it. So that can produce microplastics. One of the funny things about some of these bottled water studies is that pristine sources, so sometimes they'll add that they don't treat it very well, were the one, and you paid more for it, actually had the higher levels of contamination. So, and the coal, the no-name brand actually was quite clean, which was interesting. So we did find an average of 77 micrometers of, and we also found a reasonable number of particles that you would drink. We also saw shards, so those push tops that you get as well. So we looked at whether there was a correlation between the push top and the type of polymers you're finding, but there wasn't really. Our take on this was actually that we didn't estimate that you were ingesting too many polymers particles from this drinking water, from this exposure source. Okay, this one we're looking at EDCs in beverages. What we're actually looking at is the same water, like Coke in cans. Well, the pressure is on, isn't it? I love it. Cans, bottles, and different types of materials. And we measured them in PFAS, bisphenols, parabens, and other things. We actually found very elevated levels of bisphenol A in particular metal canned. So tin was actually the biggest one that we found, and it was actually coconut water. And recently, and after we did this study, the US EFSA reduced the TDI by 20,000 times lower. And so we would estimate that people who were drinking those beverages would be getting high exposure to BPA from, so it was actually coconut water, imported tin coconut water, in case that's what you like to drink. Last one is, this was plastics in the environment essentially are a vector for other chemicals, like a magnet. And so what we did was we dosed our plastics with flame retardant, and then we fed it to fish over 60 days. And we saw there was a bioaccumulation. So plastics do act as a vector for the movement of chemicals. And you add this to the fact that there's near a ubiquity of plastics in fish. Now I feel so much pressure, Jules. That's fair enough. So you may have seen reports of plastics being found in basically every tissue that they've looked in: liver, heart. So in liver, they found a correlation between the plastic particles and cirrhosis. In heart, they found a relationship between heart attack, the plaque, and also a heart attack. There was a study finding it in the brain, 0.3% of the brain. I'm a little skeptical on the measurement of that one. Testicles, seminal fluid, placenta, blood. This is the study. When I first saw the heart one, I asked one of my students to take a look at whether he could find particles in his blood. And there are 100% particles in the sample of blood that he took. People argue that this is biologically implausible. We need to follow this up, but this matches what's being published internationally, that there are plastic particles in our blood. Now, the key challenge with plastic is the analytical chemistry. We have a variety of different shapes, sizes, and morphologies. Okay. We are producing chemicals at a rate we cannot assess them. This is the key message that we need to be mindful of. The federal government is essentially focused on 3 PFAS. There's 15,000 different ones. And if we're banning some, there'll be some others that have been replaced with. We need to be more proactive in how we manage this. And we also need our own processes in Australia. We shouldn't be relying on research in other countries. And so this has led the international community to make a statement such as this, that we're creating so many chemicals that we're exceeding the planetary boundary for novel entities, because what we're doing is the annual production and releases are increasing at a pace that outstrips the global capacity for assessment and monitoring. The quote that I showed you before was from 1962. So that's 60 years ago, the start of my talk. And we haven't learned our lessons. In fact, it's probably worse today than it was when Rachel Carson wrote that report. There were nine pesticides we were primarily concerned about. And now there are 310,000 industrial chemicals, and there are actually 275 million chemicals registered in the CAS database. We have PFAS in the rain at higher levels than the US EPA is suggesting is safe to drink. And so I'm going to finish with a quote. And the question is whether any civilization can wage relentless war on life without destroying itself and without losing the right to be called civilized. Thank you very much for your attention. I'm happy to take questions.